check this out, which is a fogger. Okay, the idea is that it produces the steamed fog, which is used on the parties and in the filmmaking. And so the idea is that there is some liquid which you put it inside, special liquid, which is actually quite expensive. But then it, what it does is that, not sure what it does. Anyway, so there's a button, one button on the remote controller, and if you do this, of course, it has nothing to do with you understanding computer science, but I thought it would be pretty cool to show you that one more time. Hello everyone, welcome to Computer Science 227, lecture number 20. Okay, today we'll be talking about binary search trees, and today I'm going to explain you a very, very important algorithm of deleting a node from the binary search tree. Okay, yeah, cool. Okay. Let's get to it. Yeah, binary search tree. Today we'll be discussing binary search tree. Keep in mind that we're going to have a midterm on Thursday. Okay. Now, what is a tree? Again, so tree is a data structure with the root value and subtrees. Okay, and it can contain any number of children, right? Any node can contain any number of children. Technically, when we're talking a binary tree, though, that's a tree, specific case of a tree when each node can have at most 2 children, and no more than that. Okay, it can be 0, can be 1 or 2, but not more than that. Now, I installed the extension which is going to help me draw. So let me try that. The size. Okay. Yeah. Okay. So let's say that's 1 children, second children. Sorry. That's root. 1 children, second children, third children. Okay, and let's say we have like this 3 guys, okay, and we connected them all like that. Okay, yeah. So that'll be a tree. Okay. However, if we're talking a binary tree, there'll be a hierarchical data structure which is either empty or consists of an element called the root. Okay, so that guy will be the root, and 2 distinct binary trees. Two. Okay, so you can at most have 2 trees, subtree. Distinct binary trees, left subtree and right subtree. Okay, so in that case, it would look like, hold on. No. Okay, quit. Am I recording? I'm recording, okay. 1 second. Yeah. So in that case, you would have a root, and you would have at most 2 children, okay, for each of the nodes. Let's say for this one. Okay. Chic. So that's approximately how you would draw that, okay? This guy has 2 children, 2 subtrees. This guy has 0 children. This guy has 2 children. This guy, and this guy, all of them have 0 children, okay? 0 nodes. Now, how would I delete all of them? Okay, perfect. Awesome. No, hold on. Okay. Okay, so the length of the path is the number of edges in the path. The depth of a node is the length of the path from the root to that node. The set of all nodes at a given level are called the set of the nodes at a given depth is called a level. Siblings are the nodes that share the same node. Root left child, right child. Okay, so we talked about that already. Binary search tree. Okay, so we said that binary search tree is a type of tree where you can pick any node. Let's say this guy over here. Okay, and then you can kind of draw a line, vertical line like this, and in this case all the nodes on the left from that line are going to have values less than the node you're talking about. Let's say here we're talking about 100. Okay, so all the elements on the left are going to be less than 100, and all the elements on the right are going to be greater than 100. Okay, so 60, 67, 55, 45, 57 are less than 100, and 107 is greater than 100. Okay, that's why for this particular node, the property of the binary search tree actually worked well. Okay. Okay. Now we'll talk about the search, how to do that. Now, today we'll be talking about deleting, how to delete a node, and that's a very usually when I explain that, it's causing some issues, like a little bit of issues for students to understand that. That's why I highly recommend paying attention to what I'll be saying today, and I'll also provide a couple of by the way, read the book. Okay, there'll be chapter number 25. Okay, so over there they're also talking about how to delete it properly, and they'll be basically giving you all the details on what I'll be talking about today. So I'll actually follow the textbook's pattern, but you can also watch some online tutorials, and I think I'll try to provide you guys a few of them. Anyway, how to delete a node. Okay, so again, let's imagine that you have a tree like that, and you want to delete this 10. You want to delete this 10. Okay. Now, the idea is this: when you want to delete a node, there are two cases possible. Okay, so the first question you should be asking yourself, like, the node I'm going to delete, how many children does it have, and what children does it have? Like, for example, if it's 2, okay, that's obvious. If it's 0, that's obvious. But if you have one child, is it the left one or the right one? Okay. To delete an element from the binary search tree, you need to first locate the node that contains the element and also its parent node. Okay, so when let's say that's your tree and you want to delete 10, okay, so you identify that, hey, I want to delete 10. You also need to locate the node before that, then the parent of that node, which in our case is 20. Okay, after that, what you need to do is this: let current, so you create a new node called current, pointing to the node which you want to delete. So the current point to the node that contains the element of the binary search tree, and a parent point to the parent of the current. Okay, so in our case, this will be current and this will be parent of the current. The current node may be a left or a right child of the parent node. It does not matter. Okay, so just don't think about it. Don't think about anything. Find the node you want to delete, find its parent, and then you have two cases. Okay. There are two cases to consider. Case number 1: the current node does not have a left child. So the node you're trying to delete does not have a left child. So over here you see you do not have a left child. Okay. So the node we're trying to delete is this guy, right? We're trying to delete this 10, and it does not have a left child. Okay. In that case, it's a bit easier to delete a node. A bit easier to do that. Okay, so that's easier when there is no 10, when there is no left child of 10. Okay, but yeah, anyway, so imagine you have a tree like that, you want to delete 10, it doesn't have any child. In this case, what do you do? In this case, you okay, yeah, the current node doesn't have a child. In this case, simply connect the parent with the right child of the current node. So if the current node doesn't have any left children, if it doesn't have a left child, you need to connect the right child, which is 16, to its parent. So where is our... Sorry, that's... No. Okay. Hold on. Okay, so this guy is current, and this guy is a parent. Okay. Now, what we need to do, we need to connect the right child of the current, which is 16, to the parent, right? So we're trying to delete the current, we're trying to delete 10, okay? And in this case, when current doesn't have any left children, we just need to connect the right child to the parent, okay? So where do we connect it to, right? So if current is the left child, so if 10 now is the left child of 20, that means we connect 16 to the left child of 20, okay? Now, if 10 was the right child of something else, then we would connect 16 to the right child of the parent of 10. Okay, so that is a very simple case. Basically, all we have to do is to replace this node we're trying to delete with this 16. Okay, now it's possible that the 10 would not have any children at all, right? It wouldn't have a left child or right child. In this case, what do? Just you simply delete 10. Okay, you simply delete 10 and that's it. Since it doesn't have any children, that would be pretty simple. Okay. One second. Okay. Yeah, that's what you do. I hope it makes sense. Again, if the node you're trying to delete doesn't have any left child, or if it doesn't have any children at all you have to do, you have to connect the right child, if it exists, to the parent. Okay, that's it. And in this case, let's see if our property holds. Okay, so for, let's say, 16. Okay, 16. What do we have on the left? Nothing. And what do we have on the right? 20, 40, 30, 27, 50, 80. Okay, so everything on the right from 16 is greater than 16. If we take a look at 20, okay, draw that line for 20. On the right we have 40, 30, 80, 50, 27. All of them are greater. And then on the left we only have 16, which is smaller than 20. So that's okay. That works. Cool. Yeah, and nothing changed for 40, 30, 80, 27, 50. Okay, so there is no point of like talking about that. So like for 40, for example, nothing changed. Something happened on the left-hand side from 40, but like it's so far away from 40. Yeah. So what happens is this: we delete in 10, connecting 16 to 20, and our final tree looks like this. Hope it makes sense. Again, this is the simplest case. Moving on. Second case number 2. Okay, the current node has a left child. The rightmost. Oh, by the way. So let's imagine even a simpler case. Imagine that 10, the node we're trying to delete, doesn't have the right child either. Okay, so imagine that 10 doesn't have any children at all, and we're trying to delete 10. Okay, so in this case, what do? You just get rid of 10 and that's it. And you don't change anything else. Then for 20, 16 didn't exist, you delete in 10, so on the left from 20 there is nothing at all. Okay, that's even simpler. Anyway, case number 2. The current node has a left child. Okay, now we need to create a couple of more pointers to make it happen. That's a bit more complicated case. So we need to create a rightmost. Okay, we need to create a node which will be called rightmost pointer. We need to create a pointer which will be pointing. Yeah, so we need to create a pointer called rightmost, and that will be pointing to the node that contains the largest element in the left subtree of the current node. Okay, so here's how it works. If let's say we want to delete this 20. Okay, so if let's say we want to delete this 20, what we need to do, okay, and there'll be our current. There will be no parent. Okay, so parent will be null. Okay, now what we need to do now, we need to find the rightmost. We need to create a new pointer, and we need to find the rightmost. Yeah, in the left subtree. Yeah, okay, yeah. So what we need to do, we need to go to the left. So we need to consider this subtree, right? So we already established that 20. If we're trying to do a 20, it needs to have the left child. Okay, we need to go to that left child, and over here in this subtree, we need to find the element which is the greatest. Okay, so where is that greatest element will be located? It's always going to be located to the furthest right. Okay, so in this subtree, the largest element, the greatest element will always be like somewhere here. It'll be 16, right? So basically we need to go to the left, okay, from 20, go one to the left, and then constantly keep going to the right, looking for the largest element, greatest element, okay. So in our case, it is 16, okay. So, and we're gonna call it rightmost. We're going to call it rightmost. We're gonna call it right. Yeah, 16. That's what I don't like. Rightmost. Okay, so 16 will be our rightmost, and then we also need to find a parent of rightmost, right? Yes. So largest element of less of 3 of the current node and parent of the rightmost. So the parent of the rightmost is 16. The parent of rightmost is 10. Hey, what happened? Parent of rightmost. Okay. And then what we have to do is this. Okay. Note that rightmost node cannot have the right child. Yeah, it's impossible. So if the rightmost has the right child, that means that right child is greater than the rightmost, which makes that rightmost is not rightmost anymore, right? So rightmost definitely does not have any right children. Okay. Yeah, so we need to replace the element value in the current node, in the node we're trying to delete, with the node in the rightmost node. Okay, so that's the rightmost, that's the current. We need to replace the element in the current node with the element with the value in the rightmost. In other words, we need to make this 20, which we're trying to delete, 16. Okay. Okay, yeah, we're making this 16. Okay. Replace the element value in the current node with the one in the rightmost node. Connect parent of rightmost node with the left child of rightmost node and delete rightmost node. What does that mean? That means so we know that rightmost node cannot contain any right children, right? It can't have a right child because otherwise it will not be the rightmost node. So, but it's possible that the rightmost has left children, right? Okay, so here's what happens. Basically, we're removing this 16, right, and we're bringing it back, bringing it up instead of the root. Okay, so that 16 becomes our root. Okay. Let me change this to black, to green. Okay. Oh, okay. Okay, yeah. So this 16 becomes our root, and the leftmost child of, yeah, and so yeah. So basically, eliminate. We're removing this 16. Okay, is that because we're bringing it up here? Now the question is, what do we have to do with the children of 16? Right? There is no right child. We already figured that out. But it's possible that there is a left child. So what do we have to do with this? We need to connect the parent of rightmost node. So we need to connect this 10 with the left child of the rightmost. Okay, so if the left child, if this guy exists, we need to connect the parent of rightmost node to this guy. So we need to make it that way. Okay. Where is the? Yeah. So we're deleting this, right? We'll bring 16 over here, we'll bring it up, and we're connecting 10 to the left child of 16. Okay. So let me provide you like probably a better example. Okay. So let's imagine that you have a situation like this. Can I zoom it in? Now it can. Yeah, that is a scheme. So you have a parent, then you have a current. So it doesn't really matter current if it is a left or right child of a parent, doesn't matter. Anyway, you want to delete current, and it has the left child. Okay, so we're not really touching the right subtree. It doesn't really matter, but we go to the left. We find the rightmost, which means which will be the greatest element in the left subtree of the current node. Okay, so we go to the left. That is our left subtree. Okay, so that's our left subtree. In that left subtree, we need to find the rightmost node. So the node which is connected furthest to the right. Okay, and by default, by the definition of a binary search tree, the node which is located to the right has the biggest value. That's why it's called the rightmost. Okay, so again, we go from the current, we go to the left, looking for the rightmost node here, which is this rightmost. Okay, so and it does not have any right children, doesn't have the right child, right? Because it cannot. Otherwise, it will not be the rightmost. Yeah, so we find the rightmost, we find the parent of the rightmost, and it's possible that rightmost has the left child. Okay, so that's before. Okay, and now what happens after? Okay, what happens afterwards is this. So from this it becomes this. Parent is still there. Current, yeah, So current is still there, but the content of the current is replaced. So the content of the current is being replaced by is replaced with the content of this guy. Okay, so the content of this guy is moving over here. Okay, yeah, the right subtree, nothing changes to that. Okay, what happens with the left subtree? You still have the left subtree, right? However, since you are removing this node, since you bring in that node up, okay, so you're deleting this node, you have to do something with the parent and with the children. So you find the parent of the rightmost and you connect it to the left child of the rightmost, if that exists. Okay, so that's why there is a connection. You see how they drew that? That's why there is a connection. I'm sure it may actually sound like very convoluted and complicated. If you do it a couple of times with some kind of binary search trees, you just need to practice with a piece of paper. Okay, do not try to, I guess, so try to understand how it works in general in your head, but definitely practice. Definitely practice. So for example, let's imagine that we have something like this, where we have this tree, 2010, and we want to delete. What do we want to delete? We want to delete 20. Okay, so let's imagine we want to delete 20. That's the node we're trying to delete. Okay, so first step is to understand, does it have the left child or not? It does. It does have left child. It's 10, and then there is an actual huge subtree. Okay, so that brings us to case number 2. What do we do after that? We need to go to the right subtree. Left subtree. So we need to go over here, and here we need to find the rightmost element. Okay, so in the entire left subtree, which element contains the biggest number? Okay, so in this case, it's 16. So we found that 16. Okay, that means that according to the rules, according to the instructions in case number 2, we need to copy the content. We need to bring that 16 up over here, since we're trying to delete 20, right? So this thing becomes 16, okay? And since we're kind of moving this 16 up over here, that means we need to get rid of that 16, okay? So what do we do? That 16, which is the rightmost, by default, by the definition, cannot contain the right child, right? So there is definitely no right child, because otherwise that right child will be greater than 16, and that right child will be the rightmost. Okay, then this 16 is possibly has the left child, which is this 14, possibly, right? Not necessarily, but possibly. And if it is true, which in this case is true, right? So this 14 is there, and you delete in this 16, right? Because you're copying the content over here. You need to do something with this 14. What do you do specifically? You connect in this 14, the left subtree of 16, to the parent of 16. Okay. Again, since you're removing this 16, you copy the content over here to the root. In that case, kind of like this link is empty, this link is empty, right? This guy like also needs to be connected to something. So what do you connect it to? You connect this 10 to this 14. Okay, 14 is greater than 10. Okay, so that's why 14 should be on the right. So that is this, and yeah, and that brings us to this over here. Okay, and let's see if it actually becomes a binary search tree. Let's draw a line like this. Okay, 16. So what do we have on the left? 10, 14. Okay, that checks out. Or what do we have on the right? 40, 30, 80, 27, 50. Okay, that's cool, perfect. What about 40? Let's draw this. 16, 10, 14, 30, 27. They are less than 40. 80, 50 are greater than 40. Okay. How about this 10? How about this 10? Okay, so 16 are greater than 10, and everything over here is greater than 10, and 14 is also greater than 10. Okay, yeah, sorry. So it should be drawn like this. Should be drawn like this. Yeah, because 14 is technically on the right from 10. Yeah, cool. Okay, so we have some time. Let me show you. Let me show you a couple of more things. Yeah, delete. Yes, that's what you will. That's what you will need to do for the homework. Okay. Traversal. Tree traversal. Okay. So there are a couple. There is something I think which we didn't discuss last time. There are 3 ways to traverse a tree. 3 ways. Most commonly known. 3 ways. I hope you remember that if you have an array traversal is in a general traversal is something where you visit each element of the data structure, let's say an array or a tree, exactly once, and let's say you want to print them out, right? So you visit each element in a case of a tree, you visit each vertex, you visit each node, okay? So you visit, for example, in this case, you visit like 16, 10, 14, 40, 30, 80, 27, 50, and you print them out, okay? So that procedure, when you visit each element of the data structure exactly once, is called traversal. Okay, cool. Yeah, so tree traversal is process of visiting each node in the tree exactly once. There are several ways of doing that. Depth first, or depth first, breadth first, and we'll be talking about it a bit later. But depth first traversal can be split into 3 categories, and that's what I want you to remember: in order, post order, pre-order. Okay, so in the in order traversal, we visit the left subtree first, okay, then the current node, and the finally the right subtree of the current node, and then we're doing that recursively. The in-order traversal displays all the nodes in the binary search tree in increased order. So for example, if we have a tree like this, okay, so the first node we're going to visit, yeah, so we call this on the root, okay, and we visit the so first off we visit the left child of the node, okay, so we go to the left of the of 16, okay, then we'll go to the left of 10, there is nothing, okay, then so in general we're going to the left child first, then we'll print out the current node, and then we'll go to the right, okay, and you do it recursively. So you go to the left, then you go to the left of the left, then you go to the left of the left of the left, and so on, right? Okay. 3 types of traversals, right? In order. Hold on. Yeah. With in-order traversal, you go to the left subtree. Okay. You print out the left. So you print out the left node recursively first, then the current node, and then the right node recursively as well. Okay, but you do it recursively. So imagine you had something like this. Imagine you had only 3. Imagine you had only 3 nodes. Okay. Imagine you only had let's say, I don't know, 10, 8, 11. Okay, so in this case, if you wanted to do in order traversal, okay, so the way I like memorizing that is I like to remember the abbreviation: left, current, right. Okay, in this case, you go to the left and print it out 8. Okay, then you go to the current node C, right, and you print it out 10. And then you go to the right child, which is 11, and you print it out. Okay, that's a very simple case. However, if you have more nodes, if you have children for 8 and 11, that makes it a bit more difficult, because this algorithm is recursive. Okay. So imagine you have, let's say, something like this. Okay. Okay. So in this case, what's going to happen is this. You go to the left from 10. Sorry, hold on. I need to think of, let's say 7. And let's say 9. Okay. You go to the left from 8, and then you don't print out 8. Since the algorithm is recursive, you also need to go to the left from 8 as well. You go to the left from 8 to 7, okay? Since the algorithm is recursive, you also need to go to the left from 7, but that doesn't exist. There is nothing there's nothing from on 7, okay? Then you go back up with C to C current, right? And then you print out 8, okay? Then you need to go to the right, or you go to the right of 9. Then you need to go to the left of 9, which doesn't exist. You print out 9. Then you go to the right of 9, which doesn't exist. Then you're done. Okay. Then you're done with these 3. Sorry, hold on. 7. No. Hold on. One more time. So you go to the left from 10. You go to the left from 8. Okay. You print out 7. Okay, then you print out 8, then you go to the right of 8, which is 9. Okay, so you go left, current, right. Then you're done with this, you climb back up and you print out 10. Okay, then you go to the right from, so for 10, right, you're done with L, you print out current element, and then you need to go to the right. You go to the right of 10, which is 11. Then you need to go to the left from 11, which is nothing. Okay. Then you go to the current of 11, which is 11. Okay. Yeah, and then you need to go to the right of 11, which is, let's say, I don't know, 12. Okay. And that's how 12. And that's how that works. So you go to the furthest element on the left, print it out, print its parent out, then you go to the right. Then you're done with this small triangle. You need to go to you need to go one step up. So one step up from that triangle, and you need to print it out. Then you need to go to the right. So that's why it's recursive. You do not print out the element on the left from the root immediately. You just go deeper and you print out the element on the left from the root, and then on the left, on the left, on the left. Okay, so that's called in order traversal. That's in order. Okay, so left, current, right. Now post order is when you print out the left subtree of the current node, then the right subtree. Okay, so L, R, and then C. Okay, L, R, C. LRC. Okay, so what's going to happen here, for example, is this LRC. Okay, so here's what's going to happen. Yeah, so we'll go to the left from 16, 10. Okay, then we'll go to the left from 10. There is nothing there. Then we'll go to then instead of printing out 10, we'll go to the right of 10, which is 14, and we'll print out 14. Okay, so L, R, and then we'll go to the current node, which is 10. Okay, so left, right, current. Okay, now we're done with this. Now we need to print out right or from 16. Okay, we'll go to 10 to 40, then we'll go left to 30, and then we print out the left from 30, which is 27, then the right from 30, which is nothing, and then print out 30. Okay, now we're done with this. We'll go to the 40. For 40, so for 40, we're done with the left subtree. We need to print out the right subtree. So we'll go to the 80, and then we'll print out 50. Then we'll print out the right child from 80, which is nothing. Then we'll print out 80 itself. Okay. Now for 40, we'll visit the left subtree. So we did 27, 30. We'll visit the right subtree, 50, 80, and now we need to visit 40. So we'll print that out. Okay. So for 16, we're done with the left subtree. We're done with the right subtree, and now, so we're done with L, we're done with R. Now we need to print out the current element, which is 16. Okay, and that'll be post-order traversal. That's how you visit all the elements exactly once in a post-order way. In order, post-order, and pre-order. Pre-order is basically when you care about yourself first. So it's current. So it's current, left, right. Current node is visited first, then left, then right. Okay, so how that works? Okay, so for example here for this guy, so current left, right would be we visit 16, immediately print that out 16. Okay, then we'll go to the left, immediately print that out 10. Then we'll go to the left from 10, nothing. Then we go to the right from 10, 14, immediately print it out. Then we'll go to the left from 14, which is nothing. Then we'll go to the right of 14, which is nothing. Okay, cool. So we're done with this. 16, 10, 14. Okay, so for 16, for the node of 16, we're done with the left subtree, with the current node, left subtree. Now we need to go to the right. Then we'll go to the right and immediately print out 40. Then from there, current left, right, we go to the left, immediately print out 30. Then we go to the left, immediately print out 27. Okay. Then for 40, okay, so yeah, so for 30, we're done with the current 30. We're done with the left 27, and there is nothing on the right. So climb back up. Okay, for 40, we're done with the left 30, 27. We're done with the current element itself 40. Now we need to go to the right. When we go to the right, immediately print out 80, okay, because current goes first. Then print out what we have on the left, 50, and then print out what we have on the right, 0. Okay, and now we're done with the entire tree. Current left, right. Okay, yeah. So you guys definitely need to practice that with some, couple of videos, by the way, and how it's done as well. Definitely, so my recommendation is this, because I'll be asking on the quiz and on the midterm, I'll be giving you a binary search tree, and I want you to traverse it in all three ways. Okay, so I prepared the video and a set of slides for you. Okay, for example, if you have something like this, if you have something like this, like that, give me in order, post order, pre-order traversal, right? So in order, what would that be? Okay, so in order. In order. In order would be left, current, right. They'll be in order. Okay, so we'll start with A, go to the left from A, B, go to the left from B, go to D, from D, go to F. Okay, so F, then current node D, then the node on the right, G. Okay, so we're done with this small tree. Then that small tree is the left subtree of B. Okay, then we'll go to the right, and then we'll go to the left. Okay, so E, L. Okay, then we're going to then we go to A. Okay, so we're done with the left subtree of A, print out A, and now we'll go to the right subtree of A. So C, R, S, so we'll go to the left of that, then we'll print out C, then we'll print out S. So that'll be in order traversal. Recursively left, then the current element, then the right. Moving on, post order, left, right current, left, right current. Okay, how does that work? Left, right current, right? Yeah. So from A we'll go to the left, from B we'll go to the left, from D we'll go to the left. Okay, so nothing to go deeper. Print out F. Okay, then print out right of D, which is G, and then print out G itself. Then print out G itself. Okay, D. Yeah, so left, right, current. Okay, now we're climbing back up here for B. For B, we're already done with the left. Now we need to go to the right, EL. Okay, so here we're gonna have EL, E. Yeah, so L, there is nothing on the right from E, so that's why we're skipping that, and then we'll go to E. So for B, we're done with the left subtree, right subtree, and now we're printing out B itself. Okay, for A, we're done with the left subtree, but we didn't do the right subtree yet. That's why we're going to go to C, then go to R, S, C, A. Okay, now pre-order traversal. That's when you print out your current element first, so current left, right. Okay, so current A, then left, go to the left B, go to the left of that D, left of that F, F, F. So again, A, B, D, F. Okay, then G. Pre-order. Okay, yeah. Then we're done with the whole D thing. For B, we need to print out the right, which means E, L. Then we're done with the left, with the A and the left subtree of A. Now we need to go to the right, C, R, S. Yeah. Cool. And I think that's what it should be, right? If I didn't make any mistakes. Answer F, D, G, B, L, E, R, S, C. Okay, F, G, D, L, B, R, C, A. Okay, A, B, D, F, G, L, R, C. Okay, I'm hoping that pre-order is also correct. Yeah, perfect. That's it. Cool. So, yeah, one more time. Do that on a piece of paper. Definitely practice with a couple of binary search trees. The idea is this: what node do you visit first? So the only difference in how you visit them is well, you saw there are three combinations of three letters, right? Do you visit do you go in order? It will be left, current, right? Okay. In post order we go left, so we don't care about ourselves, so we don't care about the current. Left, right, current. And the pre-order will go left, current. We go current, left, right. In pre-order we care about the selfish first, so we're kind of selfish. We go left, right, current. Yeah. Okay. And we're doing it recursively. Yeah, so I post a couple of videos of other guys explaining that. I think it actually it's a lot easier than it sounds. Yeah, in fact, but I know that at the very beginning it may be confusing. Yeah, cool. Okay, hope you guys enjoyed this class. Please prepare for the midterm number 2. I hope you're staying safe. I'll see you guys next time. Bye bye.